Hello, everyone. My name is Brennan Hill, University of Wisconsin-Madison. Today, I'm presenting our work on generative world models of tasks, LLM-driven hierarchical scaffolding for embodied agents. This work focuses on solving the coordination problem inherent in complex multi-agent systems. If you plan to take only one thing away from this talk, let it be this: end-to-end learning struggles in complex multi-agent systems. To address this, we propose hierarchical task environments, or HTEs. This is a framework that moves the burden of planning out of the agent and into the environment itself. We utilize large language models to dynamically generate task scaffolding and curricula directly within the world model, bridging the gap between simple behaviors and strategic team play. Let's look at why this is necessary. In domains like robotic soccer, we face a combinatorial explosion. If you look at the left side here, we have a flat multi-agent reinforcement learning problem. With multiple agents in a continuous action space, a joint trajectory space is massive. Because the reward signal, such as for scoring a goal, is extremely sparse, agent receives zero reward for 99.9% of its paths. Essentially, the problem of stumbling on a complex coordinated by random exploration is effectively zero. Our solution is to introduce HTE scaffolding. Instead of a flat search, we decompose trajectory into a sequence of subtasks: acquiring the ball, dribbling, passing, and finally shooting. By doing this, we transform a sparse reward desert into a dense reward landscape. The environment provides intrinsic rewards for completing these subtasks, effectively guiding the agents through the combinatorial bottleneck. This isn't just a theoretical proposal, though, as it tracks the trends we observed in the 2024 literature. On the left, we have implicit or flat approaches, like TI0 and MAR Levana. These rely on manually attuned curricula or word shaping to coax agency cooperation. Moved to the middle of the spectrum, we saw a shift this year towards the hybrid and symbolic methods such as HSMARL. These systems use static decompositions like hierarchical task network, HTNs, or Bayesian strategy networks to implicitly non-structure the agent's policy. We propose the next step on the spectrum, generative scaffolding. Rather than relying on static and coded domain definitions, our HG framework uses a dynamic world model driven by LLMs to generate scaffolding on the fly. This increases the degree of explicit structures available to the agent during training. A critical component of this framework is the structure is temporary. As you can see in this graph, we employ a scaffold fading mechanism. In the beginning, the blue line, the environment provides heavy guidance and intrinsic rewards. However, as the agent demonstrates mastery, we fade the scaffolding out. This forces the agent, the red line, to internalize the policy, transitioning from guided exploration to fully autonomous execution at the end of the curriculum. Let's walk through the HD framework and how it actually functions. It starts with a high-level user prompting. For example, execute a give-and-go play. This natural language goal is fed into an LLM planner, which acts as a generative world model. The LLM decomposes this high-level intent to a simple symbolic task queue. In this case, dribble, pass, and move to space. The queue is passed a hierarchical task environments API, this engine that monitors the state of the simulation. The API monitors for termination conditions and success checks. Crucially, it generates intrinsic rewards, dense feedback that tells the agent immediately when they've successfully completed a step in the chain. These rewards shape the policy that agents executing the actions. This creates a closed loop where the LLM defines a strategy and the environment trains the agent to execute it. Here is a concrete example of what that task API looks like for a give and go. The system defines specific subtasks. Pass A to B, move A to open space, and pass B back to A. We define logic snippets for preconditions, like checking if the agent has the ball, and termination conditions, like verifying the agent has reached open space. This turns abstract strategy into concrete code-level objectives. In conclusion, our work argues for a shift in how we view scaling. To scale agents, we cannot just scale the size of the dataset of the model, we must scale the structural complexity in the environment themselves. This also has major implications for sensorial transfer. Using hierarchical decomposition, isolate the domain shift to low-level motor policies, making the transfer of high-level strategies much more attractive. Finally, we demonstrated this in robotic soccer. This framework is general purpose. It extends naturally to other complex domains like autonomous driving and robotics assembly, where long horizon planning is essential. Thank you very much for your time. You can scan the QR code here to access the full paper.